In any electrical machine, for that matter any equipment, finding out its characteristics by actual experiment is very important, because although it is possible to get some idea about the performance of the equipment from the design data, but experimental validation or testing is essential. This is true also for all electrical machine and particularly for DC machines. One of the important characteristics that we test for any electrical equipment are the losses and efficiency of the equipment. The same is true for DC shunt motors. In a DC machine, there are several mechanisms or several components of these losses. So, losses can be broadly categorized into two parts. One is called the fixed loss or constant loss, another is called the variable loss. Now, fixed loss for DC shunt motor has several components. One is called the mechanical loss, assuming that the machine operates almost at constant speed, then the iron loss and also the shunt field loss. Now, in a DC machine, although the currents and voltages are DC from outside, if we look at it, we find that in the armature, if we look at any portion of the armature, any volume in the armature, the flux passing through that volume is alternating, because the armature is rotating, both due to field and due to armature reaction. Therefore, there is some iron loss present in a DC machine. The iron loss is mostly due to hysteresis and eddy current loss. Hence, it has the effect of producing a opposing torque on the motion of the machine. Hence, can be represented as a part of, sometimes it is represented as a part of mechanical loss. The variable loss is mostly the Ia square Ra and the brush contact loss. In addition to this, there is something called the stray load loss. There are several mechanisms that goes into producing this stray load loss. For example, the skin effect of the armature conductors, and then the induced iron loss in the end covers, overhangs, skin effect of the overhang. All these items goes into make a stray load loss. So, in general, the fixed loss Pk of a DC machine consists of P iron plus P mechanical loss plus P shunt field loss, whereas the variable equal to IA square RA plus P stray. Maximum efficiency of this machine usually occurs when Pk is equal to Pv. This is usually the condition for maximum efficiency. Now, let us see in the motoring and generating mode how these losses are distributed. Let us first take the case of a generator. So, in a generator, the mechanical power is input, then the first component of loss that goes out is the mechanical loss. We said that iron loss has the effect of producing a opposing torque. So, next comes the iron loss. This is the net mechanical power input to the machine, and then the developed power Pd equal to EIA. So, this is Pd from which you will have P shunt field loss going out, then you will have PV going out, and finally you will have the PO, which is equal to VT IL. This is generator mode. In the motor mode, the diagram will reverse to some extent. So, in the motor mode, the electrical power is input. The first component of loss that goes out is the shunt field loss, and then this PV. Here you get P developed equal to EIA. From there, P iron it has to overcome, and then it has to overcome mechanical losses, and finally you will have the mechanical power output. So, the generator efficiency equal to VIL VTIL divided by VTIL plus PK plus PV, and motor efficiency nu M equal to VTIL minus PK minus PV by VTIL. There are several testing methods available in order to find out the different components of the losses of a DC machine. One of them is called the Swinburne test. This is a no load test, mostly to determine the components of PK. The circuit diagram is like this. You have the machine which is rotated, you have a ammeter and a voltmeter connected, and the machine is connected to the rated supply voltage through a adjustable armature resistance, and then the field is also supplied through an ammeter and a adjustable field resistance. Now, this is the top supply voltage Vs, field current If, armature current Ia, this is the armature voltage Va. The machine is operated at no load with rated field applied. With rated field applied, if the machine operates at no load, then in the motor mode it will operate at slightly higher than the rated speed. In order to bring down the speed to the rated value, this armature resistance is included. Now, the armature reading and the voltage that it will read is the no load armature current. So, the power supplied, that is VA, reading of this voltmeter VA IA0, this is basically P ml plus Pi plus Ia0 square Ra, or P ml plus Pi equal to Va Ia0 minus similarly, P SH equal to Vf If. So, Pk equal to Vf If plus Va Ia0 minus Ia0 square Ra. In order to compute Pk, we need to find out what is Ra. This includes also the brush contract drop. So, this Swinburne test usually gives the different components of the fixed losses, but since this is a no load test, the load loss components cannot be determined, particularly the stray load cannot be determined and since this is a cold run test, the machine temperature does not rise up to the rated value, hence whatever losses we get that are conservative. And since this machine is not loaded in this case, it is not possible to predict whether the machine, the commutation of the machine will be satisfactory under load condition. So, here the estimate of efficiency that we will get from this test will be somewhat on the higher side. Therefore, in order to overcome these problems, another test method which is called the Hopkinson test is used. Hopkinson test is a load test, but also a back to back test, that is, here you have two identical DC machines mechanically coupled. And connected to the same supply. Is the DC supply. The field of the armatures, field of the machines are supplied from the same supply. So, this is motor and this is generator. So, what we do initially, this machine 1 is started as a motor and brought to rated speed by adjusting the field current. Next, the field excitation of the generator is also adjusted so that the voltage across this switch S2 becomes, they have the same polarity, and the voltage across the switch S2 becomes 0. Once it is 0, then this switch is closed. Now, what happens is that now the total current drawn from the supply will be simply the losses of the two machine, the power developed by the machine, the power consumed developed by the generator will be electrical power consumed by developed by the generator will be consumed by the motor, whereas the mechanical power developed by the motor will be used to run the generator. So, this is something like a back to back test which we have seen in case of a transformer, which is called the Shunt test. The cause effect relationships are like this: if the generator field current is increased, then that will cause an increase in the generated voltage, and it will make the generated voltage of generator greater than the back EMF of the machine, which will increase the generator armature current as well as the machine armature current. So, by controlling the generator field excitation, we can control the loading of the two machines. Similarly, if we reduce the motor field current, this will lead to an increase in the speed of the set, which will in turn increase to a generated voltage, which will again make generated voltage greater than the motor back EMF, which will increase the IAG and IAM. So, this way we can adjust the loading of the two machines. In order to compute the losses, we note that if this is the motor current and this is the generator current, then we can write the net current drawn from the supply IA equal to IAM minus IAG So, the total input the machine equal to V IA So, this is equal to total armature losses since there is no output. So, the stray load loss total equal to V IA minus IAM square stray load loss plus Pi plus Pml of both the machines. This is equal to this. So, for each machine is half of. Here we are making an assumption that the machines are identical. There is no way to accurately determine the division of these losses between the two machines. So, motor field loss equal to so total loss in the motor equal to and similarly The motor efficiency generator efficiency So, like Shunt test, the advantages of this Hopkinson test are that two machines are tested under loaded condition, so that the stray load loss component can be taken care of. Also, they can be tested at various levels of load without actually loading them. However, there are certain assumptions involved. For example, we assume that the machines are identical and the stray load loss and the iron loss, the frictional loss are equally divided into the two machines. That is one thing. And second is that the two machines losses are stray load loss etc. are assumed to be for small machine large variation of field current is normally required for to match the speeds. So, for small machine this testing do not give equal division of losses between two motors. So, two machines. So, this testing is more useful for larger machines rather than small machines. So, let us solve a few problems to find out how exactly we determine the losses and efficiency of DC machines by performing these tests. So, let us first see something with the Swinburne test. So, we have a 50 kilowatt 250 volt 1200 RPM DC motor. On no load, with Vt equal to 250 volts, the armature current is 13.24 amperes and the speed is 1215 RE. The resistance measurements and brush contract drop measurement gave you Ra equal to 0.06 ohm, Rf equal to 50 ohm, and Vb equal to 2 volts, that is the drop in the brushes. So, what will be the efficiency of this motor for a shaft output of 50 kilowatt? Assume that the stray load losses is 1% of output. This assumptions is sometimes made because it is very difficult to accurately measure this loss. The speed turns out to be at 50 kilowatt shaft load, n equal to 1195 rpm. So, from the no load test, armature input equal to 250 volts into 13.2 ampere, this gives you 2300 watts. This is the power input at no load. So, what is the rotational losses? This is equal to iron losses plus mechanical losses. This comes to the no load power input minus the no load armature copper loss minus the brush losses Now, the speed varies from 1215 to 1995 rpm. We assume that due to this small variation in speed, the rotational loss does not change. So, on load, P rotational remains same and P shaft equal to 50 kilowatt. Let the corresponding armature current be IA. Then the input power is 250 IA minus armature resistance loss minus brush loss minus rotational losses minus stray load loss, which is assumed to be 1% of the output. This is equal to 50 kilowatt. So, rearranging terms, we get IA square minus 248 IA plus 53763 equal to 0, from which we get IA equal to so input power P in plus the shunt field power is 250 square by 50, this comes to 58,650 watts, and P out equal to 50,000 watts. So, efficiency is now. If we assume that the stray load loss remains more or less constant, then actually the expression for efficiency is given by the supply voltage into armature current, which is the input, minus zero point 0.06 IA square minus the three 763, which is 1% the rotational loss plus 1% of stray load loss. This is the output power at any armature current, and the input power is 250 IA plus 250 into field current is 5 amperes. So, the maximum efficiency occurs d nu dIA equal to 0. So, this gives you IA equal to 284 amperes. So, and the maximum efficiency comes to be about 86.36%. Here we have seen that for solving this problem we had to make an assumption of the stray load loss and assume that it remains more or less constant. With Hopkinson test we can experimentally find out what this stray load loss component will be. So, let us solve a problem involving this Hopkinson test. In order to This Hopkinson test is performed on two machines. The supply voltage is 250 volt. IFM is 2 ampere, IFG equal to 2.5 amperes, IAG generator armature current equal to 60 ampere, and IA current drawn from the supply equal to 15 amperes, and RA of both the machine RAG equal to RAM equal to 0.2 ohm. Find out what is nu m and what is nu g. The generator field current is given, and we know that IA equal to IAM minus IAG. Therefore, IAM equal to IA plus IAG. This comes to 60 plus 15 equal to 75 amperes. So, what is the stray load loss plus Pi plus PML of each machine? This is equal to half of VIA minus IAM square RAM minus IAG square RAG. This comes to half of 250 into IA is 15 amperes minus 75 square into 0.2 minus 60 square into 0.2 equal to 9525 watts. The input power P in to the motor Pi motor equal to V into I AM equal to 250 into 75, which is 18,750 watts. So, total loss in the motor PLM equal to PST plus PI plus PML plus shunt field loss, which is P into IFM plus IAM square RAM. This comes to 952.5 plus 250 into 2 plus 75 square into 2 plus, this comes to 2577.5 watts. So, the motor efficiency nu m equal to the input power 18750 minus losses divided by input power, this comes to 86.25%. In a similar manner, the loss in the generator comes to 952.5 plus the generator field loss, which the field current is 2.5 amperes, plus generator armature current square into armature resistance, this comes to 2297.5 watts. Now, generator output equal to VIAG comes to 250 into 60 equal to 15,000 watts. So, new generator equal to 15,000 divided by 15,000 plus 2297.5, this comes to 86.7%. Thank you.